Vectors in the plane 13.1. Well, I'm pretty sure you have heard about vectors before, maybe whether you took a physics class or maybe you took a basic science in high school or anything like it. Well, of course, most of the times the idea of what a vector is arrows, like arrows having like a direction and to whatever point. But I mean, we're still going to stick to that idea for now. But trust me, the idea of vectors is way bigger than just arrows with pointing in a random direction. It's a really abstract concept that, well, if you're taking linear algebra, you'll see what am I talking about. So vectors are really used to describe like pretty much everything. A person can be a vector, a polynomial it can be a vector under certain condition. It's not just like a force or velocity or a direction, but we'll leave the abstract stuff for linear algebra, you'll see. So what we're going to do is define them in both in component form and linear combinations, and then we're going to do basic operations, and of course we're going to go back and forth between their numerical interpretation and the geometric representations. So what else? And of course we are going to model some problems. We're going to look at some word problems involving vectors. First of all, let's define. A vector is a directed line segment. So these vectors have a direction, a magnitude, and a direction. All right. So, for example, the line y equals x, for example, which is the diagonal line. Well, that's only a collection of points, that are on the line y equals to x. But I mean, you can plot those points in your favorite order. There's really no rule to follow a certain order. In this case, yes, we're going to talk about lines as well for the most basic case. But in this case, for vectors, well, it's going to be a little bit different. And we need to make a distinction between a vector quantity and a scalar quantity. So a vector quantity, we usually call it like this. So for example, let me write a function v of x to represent some vector quantity. But in this case, to denote that this is a vector quantity, we draw an arrow at the top of the variable to denote that this is a vector valued quantity. And well, in this case, we use the notation, for example, something random, 2x, comma, x plus 3. And in this case, these are called like angular parentheses, if you will. This is to denote that this is a vector quantity. So that's a vector quantity versus a scalar quantity. A scalar quantity, well, for scalar quantity, just any random function f of x, x cubed plus 7x plus 5, I don't know, any function that just describes a collection of points in this case in a cubic, a polynomial, or a parabola, or a radical, etc. In this case, well, these new kinds of parentheses that we have, angular parentheses, are to describe vectors, but most importantly is the arrow at the top of the variable. All right? Well, what are these vectors anyway? So for the simplest case, okay, let me draw a Cartesian plane. All right? These vectors are free entities, if you will. What do we mean by that? Well, suppose, for example, like functions. For example, when I have the family of functions y equals x squared plus c, where c is any vertical sheet. If c equals 5, well, we're going to have x squared plus 5 x squared minus 1, x squared plus 1. So we have different families of functions. We have the same shape and in different positions, but the equation changes, you know. So this is what we did with functions. With vectors, however, vectors are free. The same components, the same numerical components, regardless of what you have, you can place them anywhere. So that's why where what the freedom really means. But of course, we use a standard way to represent vectors, and in this case we call them position vectors, and we tie them to a particular location, and that location is the origin. And that's what we're gonna do for the sake of simplicity. So in the meantime, so let me draw a vector, and so this is the tail of the vector, and this is the head of the vector. It's important to know these two properties because we're going to use this when we combine vectors together. So, and of course, let's give this vector a name. We usually, of course, V for vector, and with an arrow at the top. All right. Now, so for example, this vector, how is this vector constructed? Well, so you can think of starting at the beginning of the vector at the tail, and from there move some units horizontally and some units vertically. Right? And well, let's call this A and B. Of course, I mean it could be X and Y, but since we're gonna talk about numerical vectors for now, let's call them A and B. Later, when we talk about vector valued functions, well, we're gonna introduce those X's and Y's, T's for parameters. Well, you'll see. How do we? Okay, so let's list the vector. Okay, vector V equals. So that's the first notation. Of course, a vector, just like any line, will have many points, and a vector can be described if we know 2 points. So, for example, this is very similar. If we have this vector passing through the point P, x1, y1, and Q, which is x2, y2, we can represent the vector PQ with an arrow at the top just to denote that this is a vector. Otherwise, you might have seen this notation before, PQ with only a bar. That means segment, but we're not talking about segments, we're talking about vectors this time. And to describe those vectors, all we need is to subtract the components x2 minus x1, comma, y2 minus y1. All right? Really easy to obtain vectors knowing the 2 points. Just subtract numbers. Well, so that's number one, what a free vector is, and that's an illustration of how do we find vectors, or when we have as a piece of information 2 points where that vector is passing through. But of course, well, now we are going to tie this vector to a standard location. And again, that standard location is the origin. Well, in this case, let's call it 0, if we will. Well, not 0, it's O and T. Right, it's got OT, and in this case, well, let's just call these components as X and Y. Okay, that's fine. Let's use X and Y. Okay. Now, when we tie a vector to the origin as a reference representation, in this case has the component x comma y, we call this a position vector. All right. So the origin in this case is going to be the reference point. All right? Well, coming back to the properties for vectors, so we mentioned that a vector has a magnitude and a direction. So let's talk about the magnitude. Well, not very surprisingly, I mean, look at this shape right here. We want to know the magnitude of the vector, which is ultimately the length. But if we look at the geometric shape right here, isn't it a right triangle? And well, we want to know the length in blue, the length of the vector. Question, any ideas on what mathematical formula or theorem could be useful to find this length if we think of right triangles? The Pythagorean theorem. So this is what we have here for the magnitude of the vector. It's the square root of the sum of the squares of the components A and B. I mean, it's nothing other than a result of using the Pythagorean theorem in this setting. All right? And well, we need to be very careful with the notation. So actually the magnitude is also known as the length and the norm. The term norm, you will use it more often in linear algebra and that's because of the abstractness of the subject in linear algebra. For example, in Calc 3, we're going to look at vectors in 2 dimensions, x and y, and then we're going to move on to vectors in 3 dimensions. But of course, linear algebra is about vectors in 17 dimensions, 59 dimensions, infinitely many dimensions. And I know it's very crazy. It's very crazy to think about anything beyond the 3rd dimension because it's not even... we can't even visualize that, but it's more to like define parameters, and it's also applicable in data analysis as well. When you have, like, for example, Excel, it's really a huge matrix. You have rows and columns, and well, we're not just limited to 2 by 2 or 3 by 3. Sometimes we work with really big matrices. In cryptography, you encrypt information in matrices that are, I don't know, 1,000 by 1,000. But that's beyond our Calc 3. That's more linear algebra. And in that case, well, when we talk about magnitude, that's something that we can measure. That's something that we can visualize. But because of dimension 4 and 3, we can visualize anything. Well, they use the term norm to describe such abstractness. So this is the formula to find the magnitude of the vector. Some textbooks use this double absolute value bar. Some textbooks use this single absolute value bar. So in case you look at other textbook or other resources, you may see one notation or the other. So that's why I'm just mentioning this. And be careful with the zero. So the zero vector, it's denoted this way as 0 with an arrow at the top. And that 0 vector, well, for now in 2 dimensions is 0, 0. It's really the origin. It's the coordinates of the origin. But in this case, well, we have the 0 whose magnitude, the vector whose 0 is magnitude, right? And the magnitude of that vector is 0. This is a number. It's a scalar. That's how large or how long the 0 vector is. So it's different notation. The 0 vector with an arrow at the top, and the number 0 is just the number 0. All right. Let's do an exercise. So let's consider a vector with initial point at 4, -5 and terminal point Q 1, -1. So how about first we plot the points. So P, which is 4, -5, that's our point P, and our point Q, which is -1, 1, -1 rather. Okay? But be careful how you draw the vector. The direction matters. So they're telling us that the initial point is P, which is this one right here, and the final point or terminal point is Q. So we need to draw the arrow in this direction and make sure the arrow points like this, all right? So that's the vector that passes through those points. So for part A, draw the vector PQ in standard position. So, well, what we did is draw the free vector, a vector that will have the same magnitude and the same direction as the vector in standard position. So in order to do that, we need to go to the origin and count the same number of units in each direction for the given vector. For example, here we went 3 units to the left and 4 units up, right? And I'm going to use a different color for this. So 3 to the left, 4 units up. All right, it's the same. If you see, it's the same vector. It has the same length. It's in the same direction as the free vector that we drew before. All right. Let's write PQ in component form. Well, what do we do to do that? Well, how do we do that rather? Well, so we have to point, all we do is subtract the x component, comma, subtract the y component. So in this case, the vector PQ, it's going to be terminal minus initial. It's always in that direction. Terminal minus initial. The x terminal minus x initial, which is 1 minus 4, comma, negative 1 minus, be careful here, negative 5. Okay, so 1 minus 4, that's negative 3. And 1 minus negative 5, what happens here? We can use the smile rule. Have you ever heard of the smile rule? Well, some of you had maybe. Well, what's the smile rule about? Well, minus, do you see the smile here? Smile, be positive. I know, it's very cheesy. But it's a good way to remember why negative times a negative, it's positive, right? So, and that's our vector. Isn't it consistent with what we did in our picture? 3 negative units horizontally, 4 units up, right? Find the magnitude. Well, magnitude, I'm going to use the 2 bars. That's the square root of negative 3 squared plus 4 squared. And square root of 9 plus 16. And square root of 25, which is 5. So 5 units is the magnitude of that vector. That means that if we did this paper, draw this vector on graphing paper by the scale by the centimeters, we grab a ruler, it has to measure exactly 5 centimeters. Okay? Let's see what's next. Well, of course, just like anything new in mathematics, you learn the definition, what it is, you do some numerical intuition type of thing, and then you do operations with that. Well, of course, vectors is not the exception, and we have operations with vectors, and just like numbers, we can add vectors, we can subtract vectors, we can multiply a vector by a scalar for now. Of course, we will multiply vectors together, and there's actually 2 ways to multiply vectors. One way is the dot product, and the other one is the cross product. Both have different meanings. You'll see how we're going to do that maybe next time, not today. Well, so suppose we have 2 vectors, a vector u with its components u1 and u2, and a vector v with its components v1 and v2. And c is going to be a scalar to multiply, right? To multiply those components. If we want to add the 2 vectors, we add the x component or subtract the x components and the y components. And we're going to do that same thing in 3 dimensions in the next section. All right? When we multiply a vector by a scalar, all we do is multiply the components by that scalar. That's it. All we need. That's all we do. when we multiply a vector by -1, all the implication is here, well, numerically, what it does is to change the sign of the components, but geometric, it has a different meaning. What it does is to change the direction, to send the vector in the opposite direction, as we're going to do. We're going to see in one of the examples here. So we're given a couple of vectors. Let's represent them geometrically. Oh, by the way, when it comes to adding the vectors, adding and subtracting the vectors for the geometric way, there's two ways: the triangle method and the parallelogram method. We're going to do both. Those of you who have taken physics might be familiar with this, so it should ring a bell. So we have the vectors u and v, 3, -1, and v, 1, 3. All right, so represent u and v geometrically. Well, so, and I have two Cartesian planes. Number one to do it the triangle method, and number two to do it the parallelogram method. Okay, so for the triangle method, okay, so let's plot the first vector, the vector u. So the vector u, which is 3, -1. All right. So that's a vector u. But when it comes to adding vectors using the triangle method, we will draw the second vector, the vector that we're adding to the first one, but not in standard position. So what we're going to do is start at the head of the first vector, and from there count 1 unit to the right and 3 units up. So 1, 3, and that's our vector v. All right? And then the addition of the two vectors is going to be the following: the tail of the first vector to the head of the second vector. That's why this is called the triangle method, because this gives rise to a triangle, and this is denoted u plus v. That's the addition of the two vectors, and this is called the resultant vector. All right, that's a resultant vector. All right. Let's do the same representation, the same geometric representation, but this time we're going to use the parallelogram method. Okay? And in this case, for the parallelogram method, we are going to draw the two vectors in standard form, not just one and then the other starting at the head of the first vector. So in this case, I'm going to do the same vector u. V, again starting at the origin, that's 1, 3. All right, well, we are going to generate a parallelogram here. So if I extend this like this and like that, well, I don't think it came out really nice. Do you see how we get a parallelogram here? And well, in this case, the resultant vector will be given along the diagonal inside of the parallelogram. Did you notice it's the same vector as the one we did using the triangle method? Same thing. How about we verify this algebraically? Well, let's add u plus v. That is 3, -1 plus 1, 3. Let's add the components. X's with x's, y's with y's. That's all we do. 3 plus 1, that's a 4. Negative 1 plus 3, is that a 2? Is the result right here consistent with what we have in either picture? 4 units in the x direction, 2 units up. All good? All right. Let's see what's next. Letter B, find u minus 2v. So in this case, this is where the negative is going to kick in. You'll see how is that going to work. All right. So number 1, find it algebraically and then represent it geometrically. So let's do the algebraic version first. I think that's the easiest thing to do for now. Just add and subtract numbers. So that's 3 negative 1 minus 2 times 1 comma 3. Well, so what are we going to do here? Well, let's multiply the second vector by the number outside. That's a scalar multiplication, or rather the multiplication by a scalar. Let's leave this vector alone for now. Minus 2. And well, 2 times 3, that's a 6. And well, let's subtract the component. I really didn't multiply by the negative. I left the negative outside to make it easier. So 3 minus 2, that's 1. And negative 1 minus 6, negative 7. Careful with signs here. All right. Okay, so that's our final answer for the vector in the algebraic point, from the algebraic point of view. From the geometric point of view, however, okay, let's draw the first vector. Of course, in this case we go in order. It's not like in numbers, for example. You can simply, well, do it here. When you do 3 minus 4 plus 7, you can do this. Negative 4 plus 3 plus 7. All right? When it comes to vectors, it's a little bit different in this case, so we have to we'd rather go with the order. So let's see, the first vector u, it's again, it's 3 comma negative 1. Okay? And then in this case, so let's suppose that we didn't have that negative and we didn't have that v. Well, we already did it, right? We already had it in this direction. But what we're going to do this time is, because of the negative sign in front, that's going to send the vector to the opposite direction. So instead of going 1 unit to the right and 3 units up, I'm going to go 1 unit to the left and 3 units down. All right, so I'm going to go 1 to the left, 3 units down, and I'm going to do only 1 dot. I'm not going to draw the vector yet, because that vector is only v, and in this case we want 2 of this, right? So we have to repeat the process in this case, 1 and 3. So let me use a different color for this. Alright, let me label. This is negative 2 times the vector v, and this is the vector u. Well, in this case, notice, all I'm going to do is just use the triangle method. That's my preferred method. I think it's shorter, I don't know. So I'm going to go from the origin over here. And that's u minus 2v. And what are the components of this vector? Isn't it 1 and negative 7? Yeah. Just the same way we got it algebraically. Yep. So it should be whatever we do from the geometric point of view, it should be consistent with whatever we do algebraically. For some reason you notice anything weird, double check your signs, double check the interpretation that you do for the negative sign in front of a vector. All right. So let's see what's next. Questions before moving on to the next topic? Okay. So far, so good. All right, so another definition. 2 vectors, u and v, are equal if and only if their components are equal. And two non-zero vectors are parallel if there is some scalar c such that vector u equals c vector v. Well, in other words, we have a multiple of the components of the vector, as we will see in the next example. So in the next example, it's still the same example. It's part C of the same exercise. So they're asking us to prove that the vector u minus 2v is parallel to this randomly given vector w negative 2 comma 14. Well, what about this vector? This vector we already got. We don't need to find it again. That's 1, negative 7, right? And let's put it together with the vector w, which is negative 2 comma 14. Well, are these two vectors parallel? How do we know? Well, is one of the vectors a multiple of the other, perhaps? Yeah. It is, right? Because if you look at the components of the vector w, they are twice the vectors, twice as much as the components in the first vector. So we can rewrite this as 2 times, or negative 2 times 1 comma 7, or negative 1, right? Yep, negative. Okay, and wait a minute.
Negative 2 times.
Negative 2 times. And yes, all right. Yeah. So yes, it's a vector that it's in along the same. Well, can we have not the same magnitude actually, though they're parallel, but it's just a multiple. It's negative 2 times. It's in the opposite direction and 2 times as long. Yes, it is. All right, so yes. All right, so yeah, they're both parallel. All right, let's see what's next. Oh, unit vectors. So what's a unit vector? In like any system, there's always the unit, like for example, the unit for the real numbers, the unit for the numbers is the number 1, or the unit for our currency is $1, So in this case, we're going to find a unit vector, which is a vector whose magnitude is 1 unit. And what do? All we do is divide the components of the given vector by its magnitude, all right? And here is a notation. When it comes to unit vectors, we have a special notation for them. We have this little hat right here. It's very tiny in your paper and in the screen here for whatever reason, but that's how we will denote. Okay, so given the vector 5 comma negative 3, find a unit vector in the direction of v. So number 1, to find the unit vector, we need to find its magnitude. 5 squared plus negative 3 quantity squared. That's going to be 25, square root of 25 plus 9, which is 34, right? The square root of 34. Well, so how do we obtain a unit vector? So unit vector v with a hat, that's the components of the vector. So the actual vector 5 comma negative 3, and divide by square root of 34. Okay, and let's just distribute, if you will, this denominator. 5 over the square root of 34, comma, negative 3 over the square root of 34. All right? And this is a good answer. This is fine. I know maybe back in Calculus 1 or even in certain problems in Calculus 2 you were asked to rationalize those denominators, right? Sometimes it takes a minute to do, not too long, but for Calc 3 we're good with this answer. No need to rationalize denominators. And I think, I'm hoping my MATLAB doesn't get too picky about it, but I think my MATLAB is fine with it. All right. So as for unit vectors, and well, this will be this special unit vector that we are about to talk about. That's what is going to give rise to another vector notation that we commonly use, and I think that's the one the book uses the most, besides the angular parentheses in here. All right, and well, these special vectors are the vectors I and the vector j. And well, of course, when we look at vectors in 3D, in the next section, we're going to add the third vector, vector k. For now, let's talk about these two. And this is the vector. Okay, so let me draw real quick the graph of them. It's a vector whose magnitude is 1. So this is the vector I. In the x direction, its magnitude is 1. That is the vector 1, 0, and j is the vector 0, 1. Or rather, I was supposed to do this in the other direction. Actually positive. I and j. And then we're going to look at I, j, k in 3 dimensions in the next section. Alright, so let's express a vector. So let's use the new notation so you can see how this looks like. Express, number 1, a vector that passes through the points 1, -2 and -2, 0. And in this case, be careful. When it comes to finding the vector, we have to be specified which point is the initial, which point is the terminal, because if we're just given 2 points, that doesn't mean anything. Those 2 points are just useful to find the equation of a line, the slope, and just that. Not a vector, because we don't know which one is the initial, we don't know which one's the terminal. So notice the wording of this type of problems, right? It's very, very specific to do that end, all right? So, okay, let's find the vectors. The vector that passes through this initial and this final. -2 minus 1, isn't that -3? And -2 minus -2, which is +2, isn't it 0? Oh, what am I doing? Yeah, I think I was looking at this -2. Yeah, so it's 2, right? I was looking at the x from the second point. Okay, so that's the vector in component form. Let's express this vector as a linear combination of I and j. Well, what do I mean? What do we mean by a linear combination? So this vector right here, x direction, and this is the y direction, or component. Maybe I should use the word component. Direction is fine. All right. That means that this is related to the vector 1, 0, and this is related to the vector 0, 1, right? The vector that describes a unit vector in the x direction and y direction respectively. So what we're going to do in this case is write v -3 times 1, 0 plus 2, 0, 1. All right? So if we perform this addition of vectors right here, -3 times 1, -3 times 0, that's going to give us -3, 0, isn't it? And 2 times 0 is 0, 2 times 1 is 2. And then combine these together, don't we get back the original vector? But in this case, we are like expanding the vector into a linear combination of these two new vectors. And instead of using 1, 0 and 0, 1, we're going to use the new notation, the I and j notation. 3i plus 2j. right, guys, one quick note about notation. So vectors usually, I think almost all the time are denoted with bold case letters. That's what we have for vectors. Of course, when I'm drawing vectors, I cannot do this all the time, right? Because it's gonna take me too long. So in practice, when we're writing vectors, we write the letter I with a hat in between, J with a hat. That's to denote vector. We're gonna do that later with other type of vector functions and the like. All right. So that's the new notation for vectors. 3 units in the I directions, 2 units in the J direction. Another way to say X and Y, if you will. All right. For letter C, if U equals I plus 5J, express W equals 1/2 V minus U in both component form and as a linear combination of unit vectors. Well, so we already found this vector V, which in this case is V equals to, it's -3, 2. That's a -3, 2. And the vector U in this case, well, we're given the vector U, which is, let me use the other notation, 1, 5. All right. So what they want us to do is do this operation and then represent it in IJ notation. That's all they want. So W, which is 1/2 U minus U, 1/2 V minus U. That's 1/2 vector B, which is -3, 2 minus 1, 5. And well, all we do, multiply each component in the first vector by 1/2, and then whatever we get, subtract 1, 5. So that's going to be, okay, so that's -3/2. 2 times 1/2 is 1, minus 1, comma 5. And well, -3/2 plus 1, or rather minus 1, is in that -5/2. And 1 minus 5 is that -4. So that's the new vector. But what they want us to do is to write it as a linear combination of unit vectors. And linear combination of unit vectors means the IJ notation. So that's a -5/2 I minus 4 J, and that's final answer. Questions about it?